All right, here's 9-6 day 2. And you may not have even known it, but I kind of left you hanging with that horse problem from day 1. I mean, I didn't leave you hanging in the sense that we didn't get a solution. We did. There's 336 different ways that those 8 horses could come in first, second, or third. Okay? I didn't go all the way to this formula. Okay? This is really what was going on. Okay? We had seen in day 1 that n factorial is how we deal with permutations. Like how many different ways or how many different arrangements, if we mess around with the order, could those outcomes happen? Okay? Here's what was going on. Because R is the number of elements that you're taking. This one actually applies perfectly, and it's really what I was using, even though I didn't show my work that way. We had 8 horses, and we were just taking 3, because we were only concerned with the first 3 places. So if I went with this approach, I'd have 8 factorial over 8 minus 3 factorial, which would be 8 times 7 times 6. I'm fully aware we already solved this problem, but I want to show you this formula would work perfectly, as those 5 factorials will cancel, and if you go back and check your work, that's how we got it. And that's why we took 8 times 7 times 6, that again got us to that answer of 336. But that's really what was going on. That was a permutation where we were only taking a smaller set of the elements that we had. I think this is one of the trickier little formulas that we work with, because it involves kind of a tricky little case. It's where you're doing a permutation, so you're looking at the number of different orders that your objects could take. But what if you have objects that you can't tell the difference? Okay, that didn't apply to the horse problem because we had 8 different horses in the race, and I'm assuming there was some way to identify all 8 and we could tell them apart. What if you have objects where you can't? Okay. So it's a permutation, so it should be no surprise here that n factorial is going to be on the top. But down on the bottom, we take n sub 1. Remember, that's like your one kind of object, right? However many ways that could occur, take the factorial of that, times n sub 2, n sub 3, the number of different objects that you can't distinguish from each other, you may not be able to tell, all the way up to n sub k. Okay? That, who knows how many times you'll have that on the bottom. That's how many objects that you have that you can't tell apart. That formula is definitely going to need an example. Okay, and here we go. So, how many different ways could you rearrange the letters of the word banana? Okay. We did one like this that had 6 letters, if you looked back into day 1. But we used the first 6 letters of the alphabet, and I think we saw there was 720 different ways. Okay? But here's the deal. Banana has letters that we can't tell apart. Okay? It's got letters that are the same. The other one we did, all 6 letters were different. So for A's, we have 3 of them. N's, we have 2. B's were fine. I just have 1 of those, right? Notice all those add up to 6. Okay? But I'm relating this back to the formula that you just saw, that each of these kind of objects that have multiple that we can't tell apart need to add up to 6. All right, so up on the top, we do start with 6 factorial. And if it were just a regular permutation, that's the end of the story. And we would just number crunch 6 factorial. Except, I got to factor in now that these A's, I can't tell them apart. You know, I'm not going to have like A sub 1, A sub 2, A sub 3. If I did that, now they're distinguishable and I could tell them apart. But if I don't do that, I can't tell the difference. So down on the bottom, for my A's, I need a 3 factorial. For my N's, I have 2 of those that I can't tell apart. I need a 2 factorial. If you just have one of a certain type of element, it fits the formula. For the B's, you could put, 1 factorial. But that's good to have in your notes. That 3 factorial, that is for the A's. The 2 factorial is for the B's. Whoops. Not true. Not true one bit. I hope I didn't say that earlier, that it was for the B's. That is for the N's. The 1 factorial is for the B. Okay? So we would number crunch this a little bit. We'd have 6 times 5 times 4 times 3 factorial. 2 factorial is just 2. Those would cancel, so we would have 6 times 5 times 4 over 2. Notice how much smaller the answer is when we just did the permutation for the first 6 letters of the alphabet. Okay, there's still 720 ways that you could rearrange these letters, but there's only going to be 60 that we could distinguish because we have the same letter repeating. It's a lot fewer that actually look different from each other. All right, I had mentioned this in day 1. The last 2 problems we'll do will involve this. Okay. You should notice, as we kind of dive into this formula, it looks like a permutation, except we get a big factor of r factorial on the bottom. Which actually really reduces the number we'll get for our answer, because with combinations we're saying order doesn't matter. Okay? A really common question that comes up is, how do you know if it does or not? It's usually driven by context. Okay? On all the ones that we've looked at so far that involve permutations, let's take the horse problem again. The order is a big deal. Like, you're not just going to say, hey, these 3 horses finished in the top 3. You're going to say, wait a minute. Which one came first? Which one came second? Which one came third? Different orders are a different result. That's a permutation problem. On the other hand, if you're playing cards and you get dealt 5 cards, right? This is just talking about some version of poker that you get dealt 5. The order that you get the cards doesn't matter. It doesn't change how good of a hand you have. It's a combination problem. Okay? It's a combination. This is 52C5. How many different 5-card hands can you get? So you have 52 cards. That's a standard deck. 52 minus 5 would be 47. That would just be a permutation. Okay, if the order you got the cards, if we were counting those as different hands, but we don't, instead we have an additional factor of 5 factorial on the bottom. That'll end up looking like this. 52 times 51 times 50 times 49 times 48. I'm going to hit the brakes at 47 factorial. That's that case I look for. Those cancel. 5 factorial is 120. At that point, throw it in the calculator. 52 times 51 times 50 times 49 times 48 over 120. Almost 2.6 million hands. Almost 2.6 million different hands. Okay, that's a good example of what I was talking about at the very beginning of the first day. That we call this a counting problem. right? So we need to recognize that it's 52 choose 5, because we can't just like write out every possible 5 card hand that you could get. I mean, sure we could. It'd be miserable and it would take forever. But we can still calculate how many there are pretty quickly with the 52 choose 5. All right, last one of 9-6. Putting together a team here. We have 12. We have a 12-member team. Okay. From 10 girls and 15 boys. The team is going to have 5 girls and 7 boys. How many different 12-member teams are possible? So here we basically have the product of 2 different scenarios. We have the girls, which is going to be 10 choose 5, times the boys, which is going to be 15 choose 7. Now, before we proceed with this, would you be able to recognize here that it's a combination and not a permutation? You know, when we're talking about, say for the girls, we have 10 swimmers to choose from. We're going to pick 5. Is it clear why the order that they're picked doesn't matter? You know, the same 5 girls would consist of that team. We don't care about the order that they were picked. To have a different outcome, we'd have to take one of those swimmers and remove them and add a different one to get what we would call a different team. It's the equivalent of order not mattering, and the reason we're going to do a combination. This would be 15. Take away 7 would be 8 factorial. Going to need some room to number crunch here. We'll go 10 times 9 times 8 times 7 times 6 5 factorial is 120. I'm going to leave that one because those will cancel. 10 times 9 times 8 times 7 times 6 over 120. That would be 252. And then I might have to scoot this over here for the boys. Theirs is going to get stretched out a little more. $11 times 10 times 9, and just barely got it in there. I want to go down to 8 because that's going to cancel with 8 factorial. So we got that. 7 factorial, by the way, that's 5,040. So we could number crunch all that and get 6,435. Interesting to see that there's only 5 more boys to choose from, but it leads to significantly more possibilities, even though they're actually, well, they're choosing more swimmers too. Multiply those together, and there are over 1.6 million different 12-member teams that we could come up with given those circumstances.